Welcome to CE Voices, a series of interviews brought to you by Chemical Engineering. These insightful conversations cover a broad range of topics that are of interest to professionals in the chemical process industries.
I'm Scott Jenkins, the senior editor at Chemical Engineering. Our guest today for the Take 10 is Rajiv Narang, the director of IHS Markit's Process Economics program. Rajiv, thank you for being with us today.
Thank you, Scott. It's a pleasure to be out here in these times.
Great. Rajiv recently authored an article on the challenges associated with operating plants at Turndown, and it's generated some discussion. So we thought we would get some additional perspective and insight from Rajiv on this topic. So to start out, Rajiv, can you just tell us kind of what prompted you to put the article together?
Yeah, these thoughts have been with me for a long time on how to handle the turndown, but articulating them in an article at this time did spark a huge interest in my community, at least. So plants all over the world are being forced to operate under turndown due to demand destruction or logistical issues caused by the pandemic. Mm-hmm. And individual equipment specialists and technology companies have voiced their concern in private and public conversation. So these are the thoughts which came to me, and then I put it on paper, and we have an article. So that's where we are.
Great. So is there sort of a standard definition for what operating at Turndown even means?
Unfortunately, no, Scott. Every project, every design company has this design basis standard or a guideline, which defines a lot of things like design margins, hours of operation, feed and product specifications. But Turndown is dismissed in a single sentence, and which typically we'll read: plant should be capable of operating at 50% of design capacity, or whatever percentage you want to. Now, what does that mean? For the equipment, for the plant, and for the engineer? That is something still up in the air. Yeah. Well, not up in the air, but it kind of pushes an engineer to interpret that statement and specify the equipment accordingly. It challenges them.
Mm-hmm. So under what circumstances typically would plants, you started to mention some of these, but where situations where CPI plants would have to operate under those conditions?
On a consistent basis, not very often. In fact, the operator wants to run to the plant at about 110% capacity. And there's a lot of credit given to operators who run at more than 100%. But that's a separate issue. We can talk about that. Mm-hmm. The challenges come when one has to run under turndown due to an upstream or a downstream constraint, like a market condition, feedstock availability, or an equipment at the plant which has now bottlenecked, which is down and now bottlenecked the plant. The present pandemic conditions are challenging to plants to run under turndown conditions. And there are recent news items also to show that sweeter crude oils with reduced sulfur content are posing challenges to, let's say, a sulfur recovery unit. So a change in feed conditions or compositions or demand drive the plants to operate under turndown consistently.
Mm-hmm. So in the article, you talked about over-designed plants. Excuse me. Can you kind of explain how design margins play into that?
Okay. A design margin is a very important part of specifying the equipment and the plant, and is given huge importance during the early plant design and construction. At the engineering stage, when the design, the EPC or the construction engineer and the vendor, they can potentially build in margins which they may or may not declare. These margins come into play when the plant needs to operate under turndown on a consistent basis. Each equipment or system has an inherent turndown, which then comes into play when you want to turn down the plant. For instance, a centrifugal compressor will have an inherent turndown of about 70%. And then the anti-surge system comes in. To operate the compressor on a consistent basis at 50% with the surge protection or spill back always open, it creates its own problems. And we are, by the way, we are not even talking about how the operation away from the best efficiency point for which it has been designed. I mean, those pose a problem of their own for less efficient operations.
Yeah. So you mentioned compressors. Could you talk about finding bottlenecks in plant turndown by looking at individual pieces of equipment?
Yes, we can. And in fact, centrifugal compressors, which I just mentioned, some people say reciprocating compressors have, with the unloading valves, have a better turndown ratio. But then again, you ask an equipment specialist, and he will tell you operating a reciprocating compressor on a consistent long-term basis with valves unloaded, not good for the machine. Or a pump with the spillback protection will cavitate if you operate it long enough, and without the spillback being cooled. In fact, it has happened to me in a plant. A simple water pump, a small water pump, you put it on, I went away to the canteen, came back, and the pump was cavitating. So these things do happen. Mm-hmm. Similarly, for distillation columns, control systems, reactors operating with reduced flows can have maldistribution, and these are well known, that the distribution problems under turndown in reactors are problematic. Heat exchangers under turndown now have excess area, heat transfer area, which can lead to depositions or poor flow regimes. At the very least, as I had said before, systems operating away from the design of best efficiency point will pay the penalty in higher specific utility consumptions or higher specific emissions.
Mm-hmm. Yeah, so that's brings up another topic, the emissions. So maybe you could talk about some of the factors that make it difficult to meet emissions targets when you're operating at these conditions.
That's right. I mean, the emissions will rise if the equipment or system is operated away from the design point. At some point in the system, whether it's being supplied utility or if it is a pollution control equipment. These emissions arise, as I said, from higher specific utility consumptions at the very least. At the other end, if the plant has limits on its emissions, then those can be exceeded too. It depends how the emission permits are worded. Some permits allow short-term deviation from an annual or a longer time limit, but these are gradually disappearing. For instance, flaring during startup or plant shutdown is no longer an acceptable practice. Mm-hmm. Regulations only allow flaring during a safety-related upset. Right. So here is where a turndown scenario planning has an additional advantage. Keeping an eye on turndown also helps plan for startups and shutdowns and vice versa.
Right, yeah, that makes sense. So maybe you could start talking about some of the approaches that plants might use to try to avoid some of these difficulties that are associated with turndown operation.
Right, and it's important to keep an eye on the turndown capability of each equipment or even a subsystem. Tracking or specifying the requirements during design phase, purchase of the equipment, installation and operation. Each phase of the plant construction will help operators to avoid the difficulties when they're asked to operate on turndown. In other words, explicitly track the margins and the turndown performance of each equipment of the system. Mm-hmm. And more importantly, educate the operators on how operating away from the design point affects the equipment or plant.
Yeah,
I firmly believe that such a perspective at the operator level will be immensely helpful in understanding and running a plant safely and efficiently.
Yeah, good. In the article, you mentioned something you called escape routes in the P&ID review. So I wonder if you could explain what that is to people.
Okay, so this is one of the tips I think is important, that during system design, one should keep an eye on the flexibility which can be available in a plant. Ability to provide equipment or control system bypasses is one such opportunity. Ability to bypass an air cooler during a winter month, or mm-hmm. providing bypasses around protective equipment, such as guard beds. Yeah? Mm-hmm. You might get a feed which is perfectly okay, but still you have to run it through a guard bed. Why is that? Providing spare equipment is another technique. For instance, having one operating and one spare pump, which is common, designed for 120% of the flow, means each pump is 120% of the flow and 20% is the design margin, which will typically give at a 50% turndown, will give you a system of pump turndown of about 60% of 120%. Yeah? Or one can have two operating and one spare at 60%, each pump at 60%, which will immediately mean that you can operate one pump, and if that turns down to 50%, you can for the system you can go to a turndown of 30%. At best, if you run one pump, now it is designed for the best efficiency point, and you get a 60% turndown with good efficiency. Of course, this comes at a cost, both capital as also maintenance and safety. Higher the number of equipment, the bigger the chances of leakages. Higher the number of flanges, bigger the chances of leakages. So one needs to take a judgment call out here. Is the extra flexibility you get worth the money and the risk? It's a judgment call.
Yeah, definitely. So I wonder if next you could talk about kind of the importance of paying attention to this topic early on in a project or early on in the design phase.
It is impossible to overemphasize the importance of designing the plant taking turndown considerations into account. In the design basis for the plant and for each equipment, the turndown requirement must be spelled out. However, one needs to be careful using a one-size-fits-all approach. All pumps should have 20% design margin. Now that some pumps may need 50%, some pumps may need even 5%, and that's good enough for you. Not all pumps should be, or can be designed to a 50% turndown, as I just mentioned. It depends on the service, size, and the system design of the equipment. In my opinion, not enough attention is paid to this aspect early on in the project. A critical exercise needs to be done early on is the identification of turndown requirements, realistic turndown requirements on a consistent basis. Some are obvious and some not. An air cooler designed for summer conditions can operate under unrealistic turndown in winter. And these are real cases I'm citing. If this is frequent, one needs to design for the winter conditions too, bypass it or put in specific elements to operate that particular air cooler during temperature extremes. So that's where I think paying attention early on to specify an equipment, to specify the design basis and the turndown in the design basis. Keep the focus out there early in the project. Yeah.
Yep. So what about the situation where the project is already built, or the whatever the capital project is already advanced in its process, and it's comes out as being kind of over designed? Is there anything that people can do to kind of mitigate that?
In some ways, having a plant on the ground is an advantage, because now you know the scenarios which can hit you for turndown operations. When you're doing a new plant, you have to think of those scenarios and then plan for it. So this is a better situation than that. Unfortunately, once the concrete is in the ground, there's very little you can do about it. However, one can quickly check a plant to see which equipment or subsystem is the bottleneck for the turndown case. A study can be done to locate these bottlenecks and a strategy formulated to remove them at the next turnaround. So there are some advantages, but overall, one will have to look into this carefully and take away those turndown bottlenecks.
Right. So if someone listening to this wanted to learn more, what would you suggest? Some resources for them to check out?
Okay, so this is another unfortunate answer which I need to give, because there's a lot of literature which tells you how to give design margins on equipment. But there is limited literature which tells you how to identify turnaround requirements and the best solutions for those. I would suggest that a project or a plant, a running plant, should hold a workshop which involves equipment specialists, plant operators, and managers. That would be the best solution to work out the turndown requirements in a plant. I believe this will improve plant availability, increase efficiency under all operating conditions, and in fact will also reduce risk. There can be significant safety issues when operating under turndown. For instance, flame impingement on the tubes in a furnace, or pump safety during long periods of recycle. So if you can think of those scenarios, work it out in a workshop, and plan for them, I believe not only will it help you on managing the turndown better, but also improve the safety of the plant.
Yeah, that makes sense. All right. Well, what I'd like to point out right now is if you'd like to read Rajiv's full article, I'd encourage you to visit the online exclusive section of chemengeonline.com. Rajiv, thank you so much for joining us today.
Thank you, Scott. It was a pleasure.
All right, so stay tuned to chemengeonline.com for other videos in this series. So for now, I'm Scott Jenkins, and until next time, wish everyone well. Thanks a lot.
Bye-bye.